Hi everybody, this is the first lecture on Unit 3 of this course, and as you know, the name of the course is Theory of Automata and Discrete Mathematics. And so far in Unit 1 and 2 we've been dealing with the part of Theory of Automata. We've used machines, automata, to work with formal languages. We use automata to perform lexical analysis and syntactical analysis, which are two of the phases that we need to perform in order to execute programs in our computers. And both units were closely related because as you are practicing in your lab sessions, you need first to construct the lexical analyzer, and then the tokens that are found by the lexical analyzer are sent to the syntactical analyzer, and then you construct the parse tree and all that. So those two units were very closely related. Now we have a third unit which has to deal with graphs, and you will see that it's not so closely related to the first two units. In fact, this is the unit that has to do with the discrete mathematics part of this course. We would like to have more time to talk more about discrete mathematics. For instance, combinatorics is another very important part of discrete mathematics that you may need in computer science, for instance, to analyze the behavior of different programs, how many steps you need to perform in order to solve a task and things like that. But unfortunately, we have no time to have a unit on combinatorics or in other discrete mathematics topics. So we have selected graphs as the probably most important topic that we can cover here in this course related to discrete mathematics. Okay, you will see that it has many different applications in both in computer science and outside of computer science, and you will find graphs almost in every other course that you are going to take in some way or another. Okay, so we are going to deal with these graphs. First, I would like to explain what is discrete mathematics, because maybe you are interested in knowing why we call this part of mathematics discrete. What is this word discrete? Well, discrete has to do with, or discreteness has to do with the separation of elements. And what does that mean? Well, it's kind of the opposite of continuous. When you have something that is continuous, for instance, the real numbers, between two values you always have many intermediate values, an infinite number of intermediate values. So for instance, between 0 and 1 you have an infinite number of real numbers. Okay, but when you are dealing with discrete mathematics, with discrete structures, you have elements that are separated, completely separated. There is nothing between them. So for instance, when you are working with natural numbers, there is nothing between 0 and 1 or between 1 and 2. Okay, there are no intermediate values. And that is important in computer science, because we know, as you know, we work with digital systems that are based on 0-1 elements that can be in either state 0 or state 1, but there are no intermediate values. Either the system is in state 0 or it is in state 1, but it cannot be in an intermediate value. Okay, so that's a discrete system, and that's why discrete mathematics are important, very important for computer science. And as I've told you, there are many other topics that we could cover when talking about discrete mathematics, but we have no time, so we are going to work only with graphs. Okay, so let me start by talking a little bit about the historic development of the theory of graphs. Okay, because it's very interesting, and it's also related to a problem that we will study in the future in the lectures of this unit. Okay, and it has to do with an interesting problem or pastime, and you will see that in graph theory and in discrete mathematics in general, there are many topics that were born from mathematical games or from mathematical pastimes. Okay, so it's interesting to know where this all comes from, and to know how discrete mathematics developed and graph theory developed from just a game or a mathematical riddle. Okay, so the idea or the history is that in Königsberg, this city in the Prussian Empire, there were a number of bridges. There were 7 bridges that were connecting the two parts, the two banks of the river. Okay, so we had this river which was called Pretzel, and it had 2 islands, you can see in the figure, island C and island D, and they were connected by bridges between them, and also to the river banks, to river bank A and river bank B. And the people who lived in Königsberg were intrigued by this game or this riddle. Is it possible to cross all the bridges just one time, and to use all the bridges exactly one time, without using any bridge twice, or without leaving any bridge without being crossed? And they were interested in knowing the solution to this question, but they were not able to find a way to cross all the bridges one after the other, without repeating any bridge. But they also were not able to show that it was impossible. Okay, so there was no way that they could find to cross the river, the bridges just one time every bridge, but they also weren't able to prove that it was impossible. Okay, so this game came to be known by the great mathematician Leonhard Euler, who immediately began to think about the solution to this problem. Okay, and Euler thought about the game, and he realized that the only thing that was important in this game was that we had four different places. Here we had the riverbank A, the riverbank B, and the riverbank C, so the island C and the island D, and they were connected somehow. Okay, so we had 7 bridges, 1, 2, 3, 4, 5, 6, and 7, and they were connecting the riverbanks and the islands as we have depicted in this figure. Okay, and Euler realized that other things in the game were not important. It was not important, for instance, the length of the bridges, or the material they were made of, or something like that. Okay, the only thing that was important was the elements, the different places, and the connections between all these elements. Okay, and he thought about this problem, and he realized that he could easily solve this game in the case of the Königsberg bridges, but also for any other kind of situation with elements connected somehow, as in the figure, or with different connections. Okay, and he solved this problem, and he gave birth to the theory of graphs, which has to do with connections. Okay, we will study the solution that Euler gave to this problem. If you want, you can think about if it is possible to solve this problem in the positive, if it is possible to find a path through the bridges using each bridge once and only once to cross all of them, or if it is impossible. Okay, and we will give the solution in a future lecture. Okay, but so far what we are interested in is in the idea of abstracting from the problem these elements, these dots that we have here, these circles that we have here, and their connections. Okay, that's what we are going to study in the theory of graphs. So this has been said in a book by the science fiction writer Greg Egan. At the beginning of this book, he states that there was a graph. This is what we are going to study. And in this graph, the only thing that was important was the way that the nodes, the circles, were connected to each other. Okay, so this is a science fiction novel. It has nothing to do with directly with discrete mathematics or computer science, but it reflects this idea of the connection. Connection is what we are going to study in graph theory. Okay, and this connection, this idea of elements that are connected to others, is everywhere. Okay, so graph theory is going to be very important because it can be applied in many different situations. In computer science, we will find graphs almost everywhere, because, for instance, when you work with data structures, for instance with trees, those are graphs. When you are working with an operating system, you have file systems which are also connected. The different folders in the file system are connected to each other, so this again is a graph. For instance, when you are working online, when you are working with websites or with networks of computers, they are also connected to each other. Okay, so the different websites link to each other, so this is again a graph. Okay, you will find graphs almost everywhere in computer science, and also they can be used to represent many practical situations. For instance, as I have mentioned, when you have networks of computers, you have connections, so this can be studied with graphs. When you have, for instance, games, for instance, when you have chess, you can think about the positions as the nodes in a graph, and the connections between these nodes are the different movements that take you from a position to another one. So in computer games, or in any kind of a study of games with different positions, you can use graphs to study the different strategies and to study the different situations in the graph. Also, for optimization problems, we will see that graphs are very important. For instance, to represent molecular structures, and also nowadays graphs are also very relevant, sadly very relevant, because when we study the contagion in different diseases, when we have a pandemic like we have now, we can study the graph of connections between different people and how they were infected by the disease. So graph theory is almost everywhere, because whenever you have elements which are connected to each other, you have a graph, and you can study the properties of the graph to learn something about your situation. You will see many examples in this unit. Okay, so we want to define mathematically what is a graph, and then we want to study properties of this graph. And mainly we are going to deal with two different types of graphs. The first type of graph is what we call an undirected simple graph. Okay, and the difference with the other kind of graph that we are going to study is that in this case, as the name suggests, we have something that is not directed. Okay, so the connection between elements has no direction. For instance, think about social networks like Twitter or Facebook, that can also be represented by graphs, in which you have relationships between the different users of the network. Okay, but for instance, in Facebook, when you have friendship between two different users of the network, this connection between the users is not directed. It means that there is the connection is symmetric. Okay, if A is friend of B, B is also friend of A. But in Twitter, users can follow each other, or users can follow another user without being followed back. Okay, so in that case, we have a direction in the connection. Maybe user A follows B, but B does not follow A. So the situation is different, okay, because when we need to represent the connection, we need to know whether there is a direction in that connection. Okay, so in the case in which there is no direction, so the connection is from A to B and from B to A also, we talk about undirected graphs. Okay, and in this case, we are not going to have a preferred direction of the connection. Okay, and the way in which we represent mathematically these undirected simple graphs is by a means of a pair of elements. We have on the one hand a set of elements that we call V, which are the vertices of the graph, and we also have another set which is what we call the edges. Okay, the vertices are the elements that are connected, and the edges are the connections between the different elements. And mathematically, this is any of these edges. The vertices can be any type of elements that you want, and they can be numbers, they can be letters, they can be computers, they can be I don't know, folders in a file system, whatever you want to study. And the connections, the edges, are always pairs of elements. Okay, and since they are non-directed, there is no direction, they are non-ordered, then we represent them with sets of two elements. Okay, so a set of two elements is an edge, and it means that in this case, for instance, U is connected with V. Okay, so one thing that you need to take into account is that, well, we have here called the elements vertices. Each element is a vertex, and the connections edges. But if you read books on graph theory, you will find that these names change a lot. And depending on the book that you are reading, maybe you find a different name. Okay, so for instance, vertices are sometimes called points or elements or nodes or I don't know, circles, or maybe a different name, okay? We are going to stick mainly with vertices and nodes, but well, you can find other names in the literature. And edges are sometimes also called arrows or lines. So, well, if you read a book on graph theory, please take into account that the names can be different, okay? So always be sure to check what the authors are calling each of the concepts that we are studying here, okay? Another thing that you need to notice is that we do not accept loops, that is connections of a vertex with itself, in our definition of an undirected simple graph, okay? We will later introduce a different type of graph in which we allow to have loops, but not in this kind of graph, okay? Also, well, I have told you that since there is no order on the connection between graphs, we are using sets of elements. U and V, it's the same as V and U, because this is a set, and the only thing that is important is the elements that are in the set, okay? But to unify the notation with the notation that we are going to use for the other type of graph that we are going to study, we are also going to represent the edges as pairs UV. And be careful, because in general in mathematics, when you see something like UV between parentheses, it means an ordered pair of elements, okay? So U is before B. But in the case of graphs which are undirected, we are going to say that UB is equal to BU. Okay, so there is no order between these elements that are connected. This is important to notice. Okay, and here we find an example of an undirected simple graph in which we have the mathematical definition of the graph with the vertices and the edges, but we also have a drawing of the graph. We are mainly going to work with figures in which we have the elements connected by lines, and this will be easier to work with in many situations. It's similar to what we had with for instance, finite automata, which are types of graphs, in which we were able to work both with the diagram and with the mathematical definition, okay? So here, for instance, we have a graph whose set of vertices is V. It has 6 vertices, the numbers from 1 to 6, and it has four edges, okay? So here, for instance, we have the edge 1, 2, which is this line here that is connecting vertices 1 and 2. We also have edge 2, 5. Oh, sorry, this is not edge 2, 5, of course. Edge 2, 5 is this one here that connects 2 and 5. Edge 1, 5 is this one here, and we also have edge 3, 6. Okay, so it's very easy to find the diagram for a graph when we are given the vertices and the edges, and also it's very easy to find the mathematical notation for the edges if we have the diagram. Okay, but notice here that the lines are undirected. So when we have a line between 2 and 5, it goes in both directions. That is important to notice. Okay, so the other definition that we are going to work with mainly is what we call a directed graph, or D-graph, okay, which is also a pair of vertices and edges, but now the difference is that we have an order in the in the connection. Okay, so this kind of graph, for instance, is adequate for representing the relationship between users in Twitter, because we can specify who follows who. If A follows B, then we write something like this, but this is different from B following A, which will be represented like this. Okay, so the definition is the same, but we need to take into account whether the graph is directed or not. If it is directed, then we have a difference between the edge UB and the edge BU. Okay, so this is important to notice because it will be very important in this lecture. Okay. Okay, so here we have another example, in this case of a directed graph. Okay, again we have 6 elements in the graph. We have 6 vertices, and we have now many more edges, and these edges are oriented. They have a direction. They are directed. Okay, so for instance 1, 2 is this edge here, but notice that now we are representing the edge with an arrow, because we want to stress that the connection is from 1 to 2 and not in the other direction. Okay, also notice that here we can have loops. We were saying before that in undirected graphs we cannot have loops, but here in directed graphs we can have loops. Okay, so for instance 2, 2 is going to be this loop here that starts in 2 and goes to and ends in the same vertex. Okay, 2, 4 is this arrow here, 2, 5 is this arrow here, and notice that we have here 4, 5 and also 5, 4. Okay, so the graph is undirected, but it doesn't mean it's directed, but it doesn't mean that you cannot have a connection between 4 and 5 and 5 and 4. But if you want to have that connection in both directions, then you need to specify both edges in the graph. Okay, we also have the arrow for 1, and finally oh, this is incorrect. This should be careful, this should be 6, 3 and not 3, 6. Okay, because 6 is connected to 3, but 3 is not connected to 6. Okay, so these are the main types of graphs that we are going to work with, and they are called simple because as you can see, there are at most one connection between each pair of vertices. Here we have, for instance, a connection between 6 and 3, but we have not 2 connections from 6 to 3. Here we have connections between 4 and 5 and 5 and 4, but only one connection in each direction. Okay, and in the previous example we have connections between pairs of vertices, but only one connection between each pair of vertices. Okay, in this case we say that the graphs are simple, and the difference is whether they are directed or not. Okay, but there are situations in which we have several different connections between a pair of vertices. For instance, imagine that you are representing the different cities of a country and the different ways in which you can get from a city to another. So maybe you have a highway, you have a railway, you can travel by plane, you can travel by ship. Okay, there you have many different ways of to go from one city to another. In that case, you want to connect the different vertices with more than one edge. Okay, That is the situation in which we call the graphs multiple. So we can have simple graphs, which are the main ones that we are going to work with, but we can also have multiple graphs in which we have more than one connection between each pair of vertices. And that is exactly the situation that we had in the Königsberg problem, because we had more than one bridge between, for instance, island C and the riverbank A. Okay, so although we are not focusing on multiple graphs, we are going to use them in some situations, for instance, in order to solve the Königsberg bridge problem. Okay, so these are what we call multiple graphs, okay, or also multigraphs. And the mathematical definition is a bit different. I'm not going to explain all the details because they are not really very important to our goals. But the idea is here is that now we can no longer represent an edge by the vertices that it connects, because there can be several different edges that connect the same vertices. So if we have a connection between, for instance, vertex 3 and 5 and another between 3 and 5, we don't know which of the edges is the one that we are referring to. So we need to give names to the edges, and then we have a function that tells us which are the vertices connected by those edges. Okay, as I've told you, this is not very important, but notice that we no longer we can no longer identify an edge with its vertices, okay, because there can be different edges with the same vertices. Of course, multigraphs can be or multiple graphs can be either directed or undirected, okay, so we have also these versions of multigraph, directed multigraph, okay, and in the literature you can find different names for these types of graphs. So again, be careful if you read a book on graph theory, because maybe the name is different in that book, okay. And as a table in which you can see the different properties of the graphs that we have defined, here you can see that we have three different parameters that define the type of graph that we are working with, whether it is directed or not, whether it is simple or not, and whether it has loops or not. We are mainly going to work with what we call graphs and D-graphs, directed graphs, and we know that these are the graphs that are simple, okay? We are mainly going to work with simple graphs. And then the difference between them is that the non-directed graph is, of course, non-directed, and the directed graph is what we call the D-graph, okay? But you can also have multigraphs, directed multigraphs, and here you can see that the only one that has no loops is the graph, or the simple undirected graph, okay? Anyway, the names, as I've told you, are sometimes different in different books, and it's a bit confusing, so I will try to specify the type of graph that we are working with, okay? So if I don't say that it is multiple, it is simple, but I will try to say every time whether it is directed or not, okay? So when we define graphs, we want to study properties of these structures in order to get an idea of the connection that exists between the different elements, or what are the properties of the problem that we are studying, or something like that. So we need to define a number of concepts that are going to be important for us in order to develop algorithms and to study properties of graphs. The first of these concepts is what we call incidence. So we say that an edge is incident in a pair of vertices if those vertices are the elements that the edge is connecting. So for instance, if the edge is UV, it is incident in both U and in V. If also the graph is directed, we say that it is incident to V, because it arrives at V, it goes to V, and we also say that V is its end vertex, and it is incident from U, because it starts in U, it goes from U to V. Okay, so U, it's the initial vertex. The names are, I think, very clear, and the meaning of these concepts, it's exactly the same as you may imagine from the names. Okay, so it's not very important or not very difficult. Okay, if the graph is not directed, then we also sometimes say that the edge joins the vertices. Okay, and then we cannot talk about end vertex, initial vertex. We say that both vertices are the endpoints of the edge. Okay. Another example here in which we can see how these definitions are stated in a particular example. Okay, so for instance here we have a directed graph with 6 vertices, and we are going to focus on vertex 2, okay, which has 3 arcs that are incident in this vertex. The arc 2, 2, or the edge 2, 2, the arc 2, 4, and the arc 2, 5. Okay, and in the 3 cases, the vertex, the edge is incident from 2, and also here, since we have a loop, in this case the edge is incident from 2 and to 2. 2 is both the initial and the end vertex of this graph. In these other cases, the edge is incident from 2 to 4, and here from 2 to 5. 2 is the initial vertex, and 4 and 5 are the end vertices of these edges. Okay, I think it's quite easy, but if you have any question, just send me an email or something. Okay. In this case, we have a non-directed graph, and we are going to focus on edge 3, 6, which joins vertices 3 and 6, and both vertices are the end points of this edge. Again, very easy. Okay. Another very important concept that we need to study, and in fact it will be key in the solution to the Königsberg problem, is that definition of the degree of a vertex. And this is a bit different depending on whether the graph is directed or not. If the graph is not directed, then we define the degree of the vertex as the number of edges that are incident to the vertex. Okay, so we only need to focus on the vertex and see how many edges are touching that vertex. For instance, here vertex 5 has degree 2 because there are two edges, in fact, edge 2, 5 and edge 1, 5 or 5, 1, it's the same because the graph is not directed, which are incident to the vertex. Okay, for instance, this vertex 3 has degree 1. Okay, again 6 has degree 1, 5 has degree 2, as we have already mentioned, 2 has degree 2, 1 has degree 2, and 4 has degree 0. Okay, so the number of edges that connect to the vertex or are incident to the vertex. Okay, in the case of a directed graph, we can define two types of degrees: the in degree and the out degree. The in degree is the number of of edges that are incident to the vertex. Okay, so these are the number of vertices, the number of edges that have the vertex as its end point, that end in that vertex, while the out degree is the number of edges that are incident from V, that start in V, that have V as their initial point. Okay, so for instance here we can see that vertex 1 has in degree 1 and out degree also 1. Okay, for instance, vertex 3 has in degree 1 and out degree 0. Okay, for instance, vertex 4 has in degree 2 this edge here and this edge here, and out degree also 2, this edge that goes to 1 and this edge that goes to 5. And the total degree is the sum of the in degree and the out degree. So for instance, for 1 we have degree 2, which are the number of edges that are incident either to or from the vertex. Okay, here 3 has degree 1 because there is only one edge that is incident, in this case 2, 3. And here 4 has degree 4 because it has 4 edges, 2 which are incident to it and 4 which are incident from it. Okay, notice for instance that vertex 2 has in degree 2 because we have one edge that comes from 1 to 2 and another one that comes from 2 to 2. Okay, and the out degree is again no, in this case is 3 because we have one vertex, one edge that goes to 4, one edge that goes to 5, and the loop that also is coming out of 2. Okay, so the total degree is 5, and notice that the loops count twice, once in the in degree and the other time in the out degree. Okay, so you need to count the loop both in the in degree and in the out degree. Okay, another very important concept that we are needing in the study of graphs is the idea of path. So far we have been working with isolated edges. We have studied an edge, whether it is incident to or from a vertex, the degree of a vertex. We have been studying just vertices and edges isolated from the others. Okay, but of course one thing that is very important in graph theory is that we can form connections of more than one edge and more than a pair of vertices. Okay, for instance, when we are studying the ways in which we can move in a city or in a country, we can use a highway to go from one city to another, and then from the second city we can take a plane or a train to go to another city. Okay, so for instance, it's very interesting to know to how many places we can go from a city, or whether all the places are connected to each other, even if they are not connected by an edge, if they are connected by a series of edges that go to intermediate vertices. Okay, and that is what we call a graph, a path in a graph. A path is a sequence of vertices and edges, so that the beginning and ending of an edge is exactly the vertex that is before and after that edge in the sequence. So for instance, here we have vertex B0, then arc or edge A1, and vertex B1. So A1 should be connecting B0 with B1. Okay, so this is exactly the idea that you may have of what is a path. Is something that lets you go from one place to another. Okay, so a path is something in a graph that lets you go first from B0 to B1, then from B1 to B2, then from B2 to B3, and we specify which are the vertices and the edges that we use. Okay, sometimes we can just say what are the vertices that we are using. Okay, so for instance, in the previous example here, we can say, for instance, that a path is the sequence of 1, 2, and then 5. Okay, and we are following first this edge and then this edge. Okay, if the graph is simple, then the sequence of vertices is enough to represent completely the path. Okay, because from one vertex to another we can only go with one edge. But if the graph is multiple, then we need to specify which are the edges that we are using to go from one vertex to the other. So in general, we need to specify the edges, but when we work with simple graphs, we don't need to do that, because there is only one way to go from one edge to the other. Okay, so in our lectures, we are going to mainly work with simple graphs, so our paths will consist mainly of just vertices. Okay, we don't need to specify the edges. Okay, an important notion related to paths is the length. Okay, the length of a path is the number of edges in the path. Okay, and notice that this length could be 0, because we consider that a single vertex, a single node, is a path. Okay, a path that takes us nowhere new. We stay in the same vertex, but technically that is also a path. Okay, so the path is not the number of vertices in the path, but the length is the number of edges. Okay, you need to take this into account. It will be important in the future. Also, a very simple definition is that we call endpoints and start point and end point, or start vertex and end vertex, the first and last vertices of the path. okay? We also say that the path is simple if the edges that we use are all distinct, okay? Notice that we can have paths that are not simple even if the graph is simple. So for